Welcome back, everybody. In this video, we'll be finishing up section 3.6 by graphing another example of a rational function, and then we'll look at something called slant asymptotes along with some examples. So let's get started with one more graph example. So for this, we have x squared plus x minus 12. It's divided by x squared minus 16. And so where we're going to start is by first factoring the numerator and denominator. So that will factor as x plus 4, x minus 3 in the numerator. And then in the denominator, we have a difference of squares. That will be x plus 4, x minus 4. So this is our first example where we have a removable discontinuity. When those factors of x plus 4 divide out, we'll see that this function is basically going to behave like x minus 3 over x minus 4, except for the fact that it is undefined at negative 4. So let's continue. Then for intercepts, as far as a y-intercept, that will be f of 0. F of 0 is negative 12 over negative 16, which is going to be 3/4. And then for x-intercepts, there's only going to be 1 because this thing won't be 0 at negative 4, right? It's just undefined there. There's only going to be the x-intercept when x is 3, right? So there will be 1 at 3, 0. And then our y-intercept was 0, 3/4. Okay, asymptotes. For vertical asymptotes, there's only going to be the 1 at x equal 4. And then for a horizontal asymptote, there will be 1 at y equal 1. Taking a look at the leading coefficients, we have x squared in the top and x squared in the bottom. Coefficient of 1 for each one, so 1 over 1 is just 1, so it'll be just y equal 1. Okay, so now that I've got some of this started, I'm going to put up a XY grid for us to work with. All right, so we've got our grid. So where I would start is by locating the asymptotes. So we saw that there's going to be a vertical asymptote at x equal to 4. So let's go ahead and draw that on. And then we'll have a horizontal asymptote at y equal to 1. Okay. And then for intercepts, we saw that there's an x-intercept at 3, 0. And then the y-intercept was at 0, 3/4. So right there. All right, so then we're going to figure out the rest of the graph. So we saw that this thing is undefined at negative 4. So at negative 4, it's going to end up having a hole. So where the kind of simplified version of f is, x minus 3 over x minus 4, let's see what that will be when we evaluate it at negative 4. So I'm going to make a new function. Let's call that g, which will be x minus 3 over x minus 4, which is basically our f without that common factor in there anymore. G is defined at negative 4. So g of negative 4 will be negative 7 over negative 8. Okay, which is just 7/8. So our function should look like 7/8, except it's going to have a little hole right there rather than being defined at that point, as we'll see. Okay, so now I want to fill out the rest of the graph. So thinking about our x-intercept. So we only have one x-intercept, and it's right here at 3, 0. And the graph has to approach its vertical asymptote. We need to check and see, okay, well, could it be going upward at this point? And so let's think about that for a second. So this is, again, going to be reasoning. So if it's going to be going upward, then that means that it would have had to kind of bounce off the x-axis at 3, 0, because it has to pass through its y-intercept at 0, 3/4. And if it was going to just bounce off at 0, 3, then, or 3, 0, then this would have had to have been a 0 of even multiplicity, and it's not. And so it can't behave that way. Another way to kind of think about it is just to check a value like 3.9 and think about, okay, what would f of 3.9 be? Or we could use our g because it's simplified. G of 3.9 is going to be 3.9 minus 3 is 0.9. And then 3.9 minus 4 is going to be negative something. Okay, and I don't need to know what it actually is. All I need to know is that it's negative, right? So right before 4, I know that this is going to be negative, so it has to be going down. And then let me go ahead and finish off the right side while we're here. I know that the 0 of the denominator that we had at 4, that has odd multiplicity, so it has to be on the opposite side here. All right, I should check and make sure that we don't cross our horizontal asymptote anywhere. So let me do that before I go any further. So let's do that down here. So our original f is x squared plus x minus 12. That's over x squared minus 16. We want to know, is that ever actually equal to 1? So let's check. So multiplying to clear the fractions out, we'll have x squared plus x minus 12 equals x squared minus 16. We'll subtract the two x squared terms from both sides. We'll have x minus 12 equals negative 16. And then adding our 12 to both sides, x will equal negative 4. So we saw that the function's not defined at negative 4. So that is especially interesting. If this function were defined, it would cross the asymptote at that point, but it's going to turn out to be just a little hole we've got there. So to answer the question, is it going to cross the horizontal asymptote out here in quadrant 1? It's not going to. All right, so then we just need to fill out the rest of this graph. Let's switch back to blue. So it's going to look basically like this. It's going to be a little hole right there at negative 4. Okay, all right. So that basically is how the graph is going to appear. There should be a little hole there right there at negative 4 where we had that removable discontinuity. Okay. All right, so there's one more new topic for this section, and that's the idea of what's called a slant or oblique asymptote. We saw that when you're looking for horizontal asymptotes, that basically you look at the degree of the numerator versus the degree of the denominator. And we saw that when the degree of the numerator was higher than that of the denominator, that there wasn't going to be a horizontal asymptote. In the special case that the numerator is degree 1 higher than that of the denominator, you get a asymptote that is not horizontal, but is slanted. And that's what this part is about. So here you'll see the slant or oblique. That's going to mean the same thing. Our book uses slant. Other books will say oblique. And so the story is this. If you've got a function f of x, it looks like p of x over q of x, defined kind of as usual. The leading coefficient of the numerator is a sub n. The leading coefficient of the denominator, b sub m. And the degree of the numerator, n is in never, and the degree of the denominator, m is in monster. If the degree of the numerator is 1 more than the degree of the denominator, then the graph is going to have a slanted or oblique asymptote, as we will see. This means that there won't be a horizontal asymptote, okay? All right, so let's check and see about finding the asymptotes of this graph. So vertical first, let's get that out of the way. Take care of vertical ones first. So that will be when the denominator is 0, so that will be x equal negative 1. Okay, so for this, there's no horizontal asymptote, right? We saw that the degree of the numerator is higher than the degree of the denominator. But since the top has a 2 and the bottom has a 1, and that's only 1 more, there's going to be a slant asymptote. So how to find that? What we're going to do, remember, we're interested in the end behavior of the graph, and so we want to see what happens for really large values of x. And so if you try plugging in values of x, you're going to see, okay, well, you get a big number in the top and a big number in the bottom, and so it's kind of hard to interpret. So what we're going to do is actually do the division here, right? Remember this fraction that you're seeing here, x squared minus x over x plus 1, is representing a division. So we're going to go ahead and divide the numerator, x squared minus x, by x plus 1. Okay, and fortunately for us, synthetic division works nicely. So you'll have negative 1 outside, 1x squared, and then negative 1x's, and then 0 for the constant. Okay. Okay, multiply and add. Negative 1 times 1 is negative 1. Negative 1 plus negative 1 is negative 2. Negative 1 times negative 2 is positive 2. 0 plus 2 is 2. So what we've done is we've rewritten our f of x so that it looks like 1x minus 2 plus 2 over x plus 1. So by doing that division, we have turned that f of x basically into a proper fraction. If you like, you can go ahead and combine these terms. If you need help doing it, let me know. But if you recombine these terms, you're going to get our original f of x. So let me just point you the way, I guess. Remember that x minus 2, we could multiply the numerator and denominator by x plus 1, right? Okay, and now that they have the same denominator, you can add. And when you do that, multiply out this product of binomials, add the 2, you're going to end up getting that original f of x that we have. Okay, so I'll leave it to you to keep going on that. So what this is good for, why do such a thing, is remembering that if we're interested in the end behavior of this graph, the slant asymptotes, we're considering values of x that are really large. So we're talking really large x's. And so if x is really big, a billion, a trillion, whatever, then 2 divided by that is nearly 0. So the thing is that this term is going to get pretty close to 0. And so our f of x will be pretty close to, sorry, let's make that thinner. Our f of x will be pretty close to x minus 2. That will be the slant asymptote. Okay, so this is a line with slope 1 and y-intercept negative 2. So that will be our slant asymptote. So I'm going to use the computer to get us a graph of this function, which we'll put in here. All right, so we've got a graph here produced by Desmos. And so the graph of our rational function is shown here in green, and you can see the kind of vertical asymptote in here at negative 1, right in there. And then there's no horizontal asymptote, but you can see as x decreases towards negative infinity or increases towards positive infinity, that the graph is getting closer and closer to this kind of purple line, which is the line y equals x minus 2. So the overall here is that we were able to long divide our numerator by our denominator in our rational function, and that gave us a linear quotient, so just a straight line quotient, and then this remainder. This remainder is a constant divided by some expression involving x. So in the end, it's going to approach 0, which is why our function eventually got close to that linear function, just the x minus 2 piece, because that remainder term approached 0. All right, so we're going to see that happen in our next example as well. Okay, so for this one, it says find all the intercepts and any asymptotes of any kind that we can find, and then sketch a graph. So let's see. So the numerator is x squared plus 5x plus 4, and the denominator is x minus 3. So for the numerator, we should try to factor that. The denominator, there's nothing to factor there. So let me get the intercepts first. So for the y-intercept will be f of 0, and f of 0 will be negative 4/3. Okay, and then for the x-intercepts, we want to set our numerator equal to 0. Okay, and so, all right, so this will factor as x plus 1, x plus 4, right? So we're going to have two intercepts, one at -1 and one at -4. So we'll have -1, 0 and -4, 0 for our two x-intercepts, and there was one y-intercept. For asymptotes, there is no horizontal asymptote. There's a slant asymptote. We'll get to that in a minute. There's a vertical asymptote at x equal to 3. Okay, and then we need to work on getting that slant asymptote. Once again, how we know there's going to be a slant asymptote is the fact that the numerator has degree 2 and the denominator is degree 1, and 2 is 1 more than 1. All right, so how we find out what it is through division. And so we're going to take and divide our x squared plus 5x plus 4 by x minus 3. And so once again, we're going to do that using synthetic division. So we've got 3 outside in the little box, 1x squared, 5x, and a 4. And then our 1 will drop straight down, multiply and add. 3 times 1 is 3, 5 plus 3 is 8, and 3 times 8 is 24, and 24 plus 4 is 28. So our original function f of x, we can write that as x plus 8 plus 28 over x minus 3. All right, and again, I'll leave it to you to check that if you go ahead and combine terms in this f of x, that you're going to get our original f. All right, so now looking at this thing, as x increases without bound, our f of x is going to get close to x plus 8, because this 28 over x plus x minus 3 term is going to approach 0. When x is getting really, really large, x minus 3 still is, 28 divided by 27 billion, right, is going to be nearly 0. Okay, so our f of x is mostly going to be x plus 8. Okay. All right, so there's enough stuff for us to get started on a graph. So let's go ahead and put down a grid for this. We have x and y intercepts. We have some asymptotes. So let's put down a grid. Okay, so now we've got our grid made, and so we're ready to start drawing our actual graph. So let's put on our intercepts first. So we saw that there was an x-intercept at -1. And then also one at -4. Okay, and then there should be a y-intercept at -4/3. Okay, and then we should put on asymptotes. So for vertical asymptotes, we saw there was only one, and it was at x equal 3. And then for our slant asymptote, it worked out to be y equals x plus 8, right? So that is a line with slope 1 and y-intercept 8. So it will pass through the point 0, 8. And then what would be a nice other second point to use? So, all right, so we could just use the slope, which is 1. So if I go to the left by 4, we'll be down by 4. All right, so that will be a good second point for us to use. All right, so there's this, right? That ended up a little curvy. Okay, so then to do the rest of this, based on where the intercepts are, we can tell that the graph is going to have to approach its asymptotes in this way. How it looks in between -1 and -4, how far up it goes, we might need to plot some more points to figure out how that goes. It's probably just relatively gradual there. The zero that gave us, well, the vertical asymptote, that zero of the denominator here at 3, it had odd multiplicity. So we know the other half of the graph is going to have to be pointing upwards towards positive infinity. And see, the other branch is going to look something like that. So this is our graph. So we found all the intercepts, and then we sketched the graph as well. Okay. All right, so I've gone ahead and put a computer graph of our last example here in the notes as well, so you can take a look at that. It did end up with just a small little bump in here, but in between -4 and -1, and that was it. So one other thing that we did not check was we didn't check to confirm that the function never intersected its slant asymptote. We saw that sometimes a rational functions graph will intersect its horizontal asymptote. Sometimes it will intersect the slant asymptote as well, but this one doesn't, and we should check that that is in fact the case. So our original function was x squared plus 5x plus 4 over x minus 3. And we want to know, is it ever going to cross the line y equals x plus 8? Okay, which was the equation of the slant asymptote. So then we want to solve this little rational equation. And so we'll multiply both sides by the x minus 3. And that will serve to clear the denominators out. So we'll have x plus 8, x minus 3 on the right side. And so then we're going to have to multiply that out. That will give us x squared plus 5x minus 24. So then you could tell if we subtract the x squared and 5x off of both sides, we have 4 equals -24, which is clearly false, right? So the assumption that the two were ever going to equal each other led us to something impossible. So what that implies is that the two graphs will never cross one another. All right, so here's our last example. We have x squared minus x minus 2 over x minus 1. So where you're going to want to start is coming up with all the intercepts and the asymptotes, and then we'll draw the xy grid and finish the graph. So pause the video and find intercepts, asymptotes, and draw the grid, and then we'll see how it comes out. All right, so this is what I've gotten so far. So we should have x-intercepts at 2, 0 and -1, 0. And then a y-intercept at 0, 2. And then there's one vertical asymptote at x equal 1. Okay, and then we'll need to put on a slant asymptote. Again, I've divided. We ended up this time with just y equal x for our slant asymptote. So that's kind of interesting. It's just a line with slope 1 and y-intercept 0. So this time it passes through the origin. All right. And so then we're ready to draw our graph. So it's never going to cross its vertical asymptote, and this one doesn't cross its slant asymptote, and I'll leave it to you to check that. And based on the points that we have, the graph is going to have to look like that. What's kind of funny or interesting about doing these graphs is that it takes so much kind of preparation work to make the graph, finding all the intercepts and asymptotes and making a little grid and all that. That takes longer than actually drawing the graph itself. So that's kind of interesting. Anyhow, that takes us to the end of section 3.7. Let me know if you have any questions, and have a great day.